In this video, we're going to build a state machine that will allow us to manage the movement of our citizens on the map. A state machine is basically a collection of states with rules about how to move from one state to another. We'll begin by creating a new script in our citizen folder called Citizen Movement State Type. This will be an enum type that labels each of the available movement states for our citizens. Let's define this script as an enum, then remove all of the mono-behavior code and place the script into our root namespace. To begin with, we will define two movement states for our citizens, idle and wander. It's important to think about the difference between these movement states and the two animation types we defined in a previous video. They both contain a value called idle, and there are some relationships between them, but they refer to very different aspects of our code. The first difference we'll highlight is that the citizen movement state type is related strictly to our simulation logic. In our simulation, a citizen will either be in the idle movement state or they will be in the wander movement state. But this has nothing to do with how they will be displayed during rendering. It is simply a description of how they are moving in the simulation. The animation types come into play when we want to display the citizen on screen. In that case, we need to be concerned about what animations are available for our citizen. Right now, the idle animation and the idle movement state will be directly associated. When the citizen is in the idle state, they will be running the idle animation. And the walk animation will start as directly associated with the wander movement state. When the citizen is in the wander state, they will be running the walk animation. But this direct relationship between the two types is only a consequence of how simple our current logic is. For instance, we will soon include collision into our simulation. And when a citizen collides with a wall while in the wander movement state, we are going to run the idle animation for a short period of time before they begin walking again. But they will remain in the wander movement state this entire time, as the animations change. So you can see that there will not always be a direct relationship between the walk animation and the wander movement state. This should begin to make a lot more sense as you follow along with the development of these states, but it's an important distinction to pay attention to now because it gets to the core of our attempt to separate our model and our view. Now we'll introduce a new script in our citizen folder called Citizen Movement State. This new class will serve as the base class for all of our movement states. It'll be an abstract base class that they will all inherit from. This will allow us to keep a single state variable that can hold a reference to different kinds of states. We will assign this variable to a new state in order to update the movement behavior of our citizens. We will eventually add new state machines to control other aspects of the entity's behavior. Let's begin by placing the class into our root namespace and removing the unity methods and base class. We will also define this class as abstract because we are never going to instantiate this base state. It'll simply serve as the template for all of our other concrete states. Now let's introduce a protected variable that will hold a reference to the citizen related to this state machine. Our movement states will be responsible for updating aspects of our citizens, so they will need access to the citizen to do this. Then we'll define a constructor that allows us to pass in the citizen for each state. Even though abstract classes cannot be directly instantiated, they will be constructed whenever a class that inherits from them is instantiated. Next, we'll define an abstract public method called tick. This method will be called on our citizen's active movement state every time the citizen responds to a tick event. This is where the logic of our movement state will run. Remember, an abstract method does not need a body to be defined because there will never be an instance of this abstract base class that can be accessed. It will only exist as the foundation of the concrete movement state classes that will inherit from it. Now, let's move over to our citizen class and begin defining the state machine. We will start by defining a read-only dictionary that will hold all of the movement states that are available for each citizen. We will use the citizen movement state type enum as a key to index this dictionary. and the values will be the instances of the movement states themselves. We will call the dictionary movement states. Let's begin by instantiating this dictionary in the constructor for our class right after setting the ID. We will fill in the two movement state types, but to complete this initialization, we are going to need to begin defining our concrete movement state classes. Let's begin by creating a script for our citizen idle state in the citizen folder. This state will be the simplest of the two. We will also create the script for the citizen wander state class as well. Let's open the idle state class and remove all of the monobehavior code, then place it into our root namespace. We also need to provide our abstract movement state class as the base class. You'll notice it is warning us that we have not implemented the required base class methods. Without doing this, our class would still be abstract. After implementing the tick method, let's include a constructor that takes in a citizen and then passes it to the base class constructor. To continue developing the idle state class, we are going to need to add a variable to our citizen class called cooldown. This variable will keep track of how many ticks the citizen needs to wait before they are able to act in the simulation again. Let's make use of our utils method called random range in order to start each citizen with a random cooldown value between 4 and 16. This way they won't all begin acting at the same time. Then let's also add a new public method to our citizen class called canAct. This will return true only if our cooldown value has reached 0, meaning the citizen has waited long enough to be able to act again. Now we can also reduce the cooldown value by 1 every time the citizen responds to a tick event. With this setup, we can now begin implementing the tick method of our idle state. We will start by checking whether the citizen is ready to act again by calling the canAct method. If the citizen is able to act, we will start by getting a new random value for their cooldown. In the idle state, the citizen will simply wait for its cooldown to complete, then it will pick a new random direction to face and reset its cooldown. So now we can use the random enum value method to pick a new direction for the citizen. Notice that none of this logic has anything to do with how the citizen is going to be rendered. We are updating the citizen's direction, but there is no logic in place that will notify the world render component that the citizen's direction has changed. It is only within the logic of the simulation that we have updated the direction. In order to update the rendering, we are going to use events just like we did when creating the citizen. Let's add two methods to our citizen class that will handle firing these events. Our movement state classes will be able to use their citizen reference to call these methods when they want the citizen to update its rendering. The first method will be named update render direction, and the second will be named update render position. Now let's introduce two event handlers to our citizen class that we can fire when these methods are called. Since these events are related directly to our citizen, we can reuse the onCitizen event args that we created for the onCreateCitizen event. We will name the first event handler onUpdateCitizenRenderDirection, and the second will be onUpdateCitizenRenderPosition. Now we can fire these events in their respective methods. In both cases, all we have to do is pass in this when creating the onCitizen event args because the citizen itself is firing the event. This is a built-in keyword that references the current instance of the class we are in. Now that these events are set up, let's return to the idle state class and call the updateRenderDirection method after we choose a new direction for our citizen. Now we can return to the citizen class and instantiate the idle state in our movement states dictionary. We can make use of the keyword this again to pass in a reference to the current citizen. Now let's copy the code in our idle state to begin working on the wander state. The logic of the wander state will be a bit more complicated than what we did with the idle state, but it will follow all of the same principles. Let's update the name of the class, and then let's delete everything within the if clause where we check whether the citizen can act on this tick. We will start the wander behavior by first getting a random direction just like we did with the idle state, but now we run into a serious complication if we hope to actually move the citizen on the map. It is possible the direction we have chosen is blocked by a solid tile. Handling this will involve introducing a system of collision into our simulation that will be somewhat involved, so we're going to go back to the citizen class and finish instantiating our movement states. Then we're going to end this video. In the next video, we will tackle this problem of collision with our map.